Good afternoon all, and thank you for sticking by till the last session. My name is Andris Freimanis. I'm a research scientist working on Integrated Computational Materials Engineering, or Icme, at VTT, the Technical Research Center of Finland. I'll introduce the Icme concept at first and then go over a few of our use cases. Now, VTT ProperTune is an brand name for an integrated computational materials engineering concept that VTT has developed over, give or take, past 20 years. It allows you to create microstructurally accurate materials, their operational loadings, and do it all in a digital and virtual space. Primarily, we use it to optimize a wide variety of material properties and product performances, such as wear and corrosion resistance, fatigue, and fracture durability, and lifetime. Now, the core concept of Icme is to provide a systemic requirements-based design approach and a digital framework for material discovery design using machine learning techniques. In VTT's ProperTune, we enable rapid development and deployment of Icme solutions. Moreover, our modules are validated. We achieve this using this process structure property performance, or PSPP principle. That's the way it looks like. Now, our customers, they mainly care about the performance of their product. For them, hopefully, they can give us some set of requirements. However, to achieve that, we need to start here. I guess this one's not cooperating. We need to start at the manufacturing process. For the manufacturing process, such as annealing in steels or sintering temperature in additive manufacturing, will change what microstructure of the material we have. We can explore it through virtual manufacturing. Now, when we have investigated the process, we optimize the microstructures because the microscale phenomena are those that will determine the macroscale properties. We do it through virtual material tests. When we have explored the microstructural behavior, we coarse-grain the lessons learned to macroscale to obtain the properties, which we can then use to optimize the performance of the products of our customers through virtual prototyping and operation. And that's the classical problem that we call the forwards problem. Start at the beginning, move forwards. More and more these days, we spend time on the inverse problem. We see some phenomena of the performance, and we need to explore it through machine learning techniques to understand what kind of a process, what kind of a microstructure caused it. We call it the inverse problem. Our ecosystem that we have developed includes all the experimental, the modeling, the validation, the digitalization activities, and our customers benefit. We decrease the time to market of new material solutions by up to 2 times. Compared to traditional trial and error. Additionally, we decrease the time required for component deployment by a factor of 2 to 3. Additionally, we have seen the return on investment by a factor of 3 to 9 across all industry sectors. Additionally, we also reduce the R&D costs, we decrease the component costs, and enable improved and disruptive discovery of new material solutions. Now, VTT's ProperTune is a tool set for solving multiscale and multiphysics modeling problems. It enables us to efficiently and rapidly set up novel modeling solutions and solvers to address materials modeling and simulation challenges. On the multiscale, we work starting from atomistics and microscale towards structural scale, where the performance of the product happens. And on the other side, the multiphysical, we work with material properties, failure phenomena, electromagnetics, chemical resistivity, transport phenomena, and so on. Now we use the data from both of these across the scales and across the physics to deliver the solution for our customers. There's a few example use cases. First, I want to note that we take information security very seriously, and all of the information that I present here are agreed by our partners. We have worked with ArcelorMittal to discover a new material solution for them. For Caterpillar, we have optimized material microstructures. And for example, for Wärtsilä, we have investigated their materials in their engines to capture and troubleshoot complex working environments. Now, for project use cases, if we think of, let's say, a simple project, and for Caterpillar, we optimized a composite coating. We could call it a typical proper tune project. We needed to improve the wear performance of the coating, and an increase of about 20% would be called significant. The problem is that R&D process with trial and error is costly and slow. And also we need to optimize and see the causal what-if scenarios. Plus, we need to deliver results fast. So this kind of a project would usually take a few months. If you go down the complexity, there's our current state of the art, which is like to design a new steel grade for ArcelorMittal. Here, the material costs needed to remain as is, and the performance needed to increase, but without changing manufacturing properties significantly. And what we targeted was the accelerated R&D process by about a factor of 2, and the step change in how the design process is performed. Lastly, our most complex, what we call our beyond state-of-the-art capabilities, are the AI-driven design of alloys. We usually develop our artificial intelligence-driven optimization loops, and the outcomes we target are production of complex digital twins or surrogate models, especially in vast design spaces, such as discovery of high-entropy alloys. Now, a bit about the optimization of coating solution for Caterpillar. You all know what a bulldozer is. It has its blade in front, right? It pushes gravel, sand, wherever we need it. However, it gets hit by little rocks, right? And the material slowly wears off. What we could do is we could hide it under some sort of a coating that is welded on. And in this case, we wanted to explore how the welding parameters impact the material microstructure and how does it improves wear performance. So that's the material matrix. It's some kind of martensitic steel. It has these niobium carbide precipitates along with boron-rich martensitic matrix and tungsten borides, tungsten boride grains. We measure these microstructures, transfer them to models, you can see it there at the bottom, and use them for simulation. When the load is applied, we can see that extensive stresses develop in the niobium carbide regions. However, lower stresses develop in boron-rich or tungsten boride-rich regions. And we can use that. The coating was welded on using either a low heat MIG or standard heat MIG method. What we saw is that standard MIG method produces greater boride phase fraction, which is beneficial influence on the impact properties. Opposite, when we compared the similar microstructures but that were produced using low heat MIG, we saw that the stresses exhibited are much larger due to lower content of tungsten borides. What happened is that low heat MIG, the max stresses were about 30 to 40% greater than in standard MIG. And with that key outcomes, we were able to increase the performance by about 40% by tailoring microstructural and manufacturing properties. The use of virtual testing enabled us to drive the R&D at much faster pace. We only spent some months rather than years on this. And we also implemented a new way to deal with the R&D process. We could do what-if scenarios, thus improving solution reliability. And the next one, the design of a new steel grade for ArcelorMittal. Now the idea here was that we needed to improve the wear resistance of this material. The manufacturer, they could give us information on these process windows. We knew what manufacturing parameters are in the window, and they could give us material properties such as prior austenite grain sizes or for grain aspect ratios within each window. And in the top model, you can see the simulation model that shows the experienced plastic strain. On the bottom one, you can see the same test, but with the whole material microstructure shown. We can explore in this way how each separate grain of the steel microstructure deforms. And that's what we did. First, we characterized the microstructures, understanding their features. We then reconstructed the prior austenite grains. We modified their aspect ratios, mimicking cold rolling, and reassembled them into new virtual microstructures. Notice the difference between original and virtual microstructure. Virtual one exhibits much more of this pancaking, the hierarchical layering of material grains, which prohibits dislocation movement, thus increasing wear performance. And we repeated this with some virtual material testing. See the bottom two videos. The deformations are absolutely massive. In the middle two, they're lower, and the best results are shown in the top two. And we can quantify damage here. On the left side, the left plot shows the normalized damage against the 1.25 sample. These numbers represent the aspect ratio, so 0.25, that's 1 versus 4. If we compare the damage at the first orange line towards the left side, that's the damage what we would call like near damage initiation. We see absolutely massive difference in the old like 125 steel grade versus newly developed 0.25. It's about 75%. So the damage near the initiation stage is much lower in the new ones. When the steady state process is reached at the second line, we see roughly 20 to 40% difference still. On the right side plot, we compare the maximum damage. And while it's somewhat similar, the lower value, 0.25, still clearly wins out. There's a bit of a mistake saying that highest aspect ratio, but it's simply because 0.25 is 1 versus 4. And well, this was basically erosion. We have similar capabilities for addressing environmentally assisted failures, such as corrosion. And we can compare the mass loss versus distance in a full-scale test. On the left side, we see that the BCFG, those are the new steel grades, while the rest were the old ones. we see that 3 of them are have better performance than the old ones. And if we compare the wear rate, we see that the current grades they have at about 0.3 grams per kilometer, while all of the new ones taken in a sufficient distance have it about 0.17. And as for the key outcomes, well, we managed to increase the performance about 2.5 times. The material cost, it remained as is, with no changes to manufacturing processes. And the R&D process was accelerated by a factor of 3, which also was applied to related costs, as about 2/3 of experiments were shifted to virtual space. With that, I'll thank you for your time, and if you have any questions, please check out our website or ask me.
All right, thank you, Mr. Freimanis. Round of applause. Yes, don't hold it in.